Okay, so welcome back to a new lecture. So we took many search algorithms, okay? But as you see, they need some, at least medium coding. You have many lines. You have to consider many stuff, okay? But there is actually similar, type of coding or similar type of algorithms that you can use, and it can also lead the robot into its goal. Okay, and can be done using something called artificial potential field. Okay, it is something like in astronomy, if you have objects in the sky, there is gravity between these objects, so it's something similar. Or for example, if you have particle charges in the atom, for example, these charges can be attracted if they are electrons with negative charge, they are attracted to the nucleus with positive charge, but at the same time they are repulsed, we can say, by other electrons because they have similar charge. So we're gonna create an environment like this. So we're gonna imagine that the map that we have that have the goal and also the obstacles, a kind of environment with some forces. These forces will repulse the robot away from the obstacles and attracted toward the goal. Okay, so we're gonna create some field, some potential field. Okay, this field has the potential to attract the robot toward the goal and move it away from the obstacles. Okay, of course it's all artificial in the map. In the real world, in the map, you don't have such kind of stuff. Okay, the robot is not a charged object, for example, or something like the earth and the sun. It's not like this. This will be all artificial. Okay, so let's see what's exactly we're gonna do with this. So you guys can see my slides.
Yeah.
Good.
Yeah.
So as I said, this is a basic idea. Oh, I have some problem here. I am very sorry for this. Oops. So it will be ugly, but that's fine. Let's see what's gonna happen. Okay. So the basic idea, if you have, for example, a very simple environment like this, okay, a robot, and this is a goal. If you remember, guys, this is a movie called WALL-E, and this robot was, dealing with garbage and trash. So it takes the trash out of a stack, then try to compress it, and put this compressed trash somewhere else. Anyways, so this is a very basic, very simple environment. You have 1D motion, so the robot just move along his x-axis. There is no y here, just x. Okay, you have a wall behind, and you have the goal. Very simple, type of environment. So what we're gonna do, we're gonna create, including, of course, a kind of force. Okay, this force or this function, we can say, has a minimum, and this minimum value will be at the goal. So, for example, if this is the function, and as you see, it's a function of x, this is the x-axis, and this function has very high values near the obstacle, and low values or its minimum value basically in that example is at the goal. Okay, good. The robot then will follow the negative gradient of this function in order to reach the goal. Okay, maybe this needs a little bit. So let's see first what's gonna happen. Then I will explain why we should, follow the negative gradient. So if I repeat this again, I'm not sure if you see, guys, the robot is just moving along this path, okay, until it reaches the minimum. The minimum value of the function is actually the goal, okay? Okay, so why then the negative gradient? So let me, share, do the sharing on the tablet so we can do it in a better way or in a more deep way. So Canvas, yes. So with a function like this, okay, the function is increasing in that way. So f of x increasing in that way.
Mr. Mustafa, I don't think we can
Yes.
see your screen for your tablet.
Okay. Yeah, okay, I will do that. Now, you guys can see it now?
Yeah.
Good. So as you see here, f of x is increasing in that way along minus x and decreasing in the direction of positive x. Okay. And intentionally, we put the goal at the minimum of f of x. And also intentionally, we put the obstacles near, the high values or maximum values of f of x. Intentionally. So what is the gradient of any function? The gradient of any function is basically its derivative with respect to x or y, whatever variable it changes accordingly. In that case, it's a function of x. So the gradient of f of x is just the derivative with corresponding to x or with x. So why we say we are moving in the negative gradient, or why we are saying that if the robot follows the negative gradient of the function, it will go to the goal, or this will lead the robot to the goal. So let's examine where is exactly the gradient is increasing. Okay, the gradient at any point is just, the tangent, the slope of the tangent at that point. So for example, let's take 3 points. Point 1 here, for example. So the tangent will be, for example, something like this. Okay, it's bad drawing, but anyways. So, and this is the slope. Let's call it slope 1. Let's have another point 2. This is the tangent. And now this is slope 2. Let's have another point 3. And this is the tangent. And we have here slope 3. What do you see, guys? You see that slope 1 is less than slope 2 is less than slope 3, right? That means the derivative, the gradient of this function is increasing in this direction. So the gradient of f of x is increasing in negative x direction. So if we allow the robot to move in an opposite direction to the increasing of the gradient, which is this, in this case, in the direction of x, then this will lead the robot into the goal. How we can say this? We can say it in that way, mathematically. Lead the robot in the opposite of the gradient means negative of the gradient of f of x. So just look at where is the direction of the increase of the gradient. For example, negative x in that example, they move in positive x. If the increment of the gradient is happening in the positive x direction, then move to the negative x direction. This will lead you to the goal. Well, of course, this may be a sloppy right now because not imaginable because we don't have codes, okay, or we don't make real examples. For example, by math, by hand, okay. So when we do that, it will be more, of course, clear. So don't worry, I will do that again with you. So let's go back to the slides. Yeah, we have the slides. Yes, no need to go to the other screen. So we have already them here. So that's fine. Okay, so if we go in the direction of the negative gradient of the function, this will lead us to the goal. So let's see what we need to do in order to create such environment, okay, for the robot. Oops. Okay, you already see that. Oops. Okay, Mr. Robot. Okay. So what we're gonna do exactly? 3 main steps. The first step is to create a function, and this is, by the way, some it's a programmer choice to create a function, and this is again a programmer choice, your choice, and this function will attract the robot toward the goal. So it can be called attraction force. And how we gonna say this? We say that because its minimum should be at the goal location. One example of these kind of functions that we can create and attract the robot towards the goal is quadratic functions. Simple, very simple example for quadratic function: y or f of x, whatever you call it, equal to x squared. This is very, very simple, the simplest quadratic functions that you can see or you can create. And if you remember, if we're gonna draw this or plot this, this is x, this is y or f of x, this is very simple function like this. It has one minimum, and this minimum at 0. So if we put the goal at 0, then, or if your goal is at 0, then this function can play such rule because it has one minimum. Okay, so the robot will be sure that if the robot go to the minimum of that function, then he will reach the goal. But basically, in our real world, our real maps, we have 2 coordinates. We have y and x. This function in here is 1D function. It's a function of only one variable, which is x. We have one coordinate. It's valid if the robot is moving in one direction only, x, for example. But generally, the robot is moving, on the ground, for example. So it have on each point 2 coordinates, x and y. Of course, generally, it may be any dimension. not only x and y even. Maybe 3-dimensional, maybe more than this. But let's, we are, very interested in 2-dimensional space. So the robot generally have x and y coordinates. Before going into that equation, let's say that the goal for 1-dimensional again, let's assume the goal is at x equal to xg. Some variable, some location called x, constant, x called xg, 1, 2, 3, 0, whatever. Okay? And this is 1D. So you can create f of x, if attraction, we can say, equal to some constant multiplied by x minus xg to the power of 2. For example, if x equal to 0, you will have this. xg, I'm sorry. You will have this. If xg equal to 1, you will have something like this. This is x, this is f of x, this is x equal to 1. So the curve will be shifted and centered at xg, which is 1 in that case. And this constant can be anything. It's a user choice. Just like you choose the function itself, you can also choose this constant. Okay? We will see it in the coding. Simply, you can put it 1. But this may lead to some problems. Okay? So you need to what's called fine tuning. You need to make some fine tuning to this parameter. This is a parameter. This constant is a parameter that you can change. But the simplest is just 1. It can also be, it may be less than 1 also. You can put it with any values, of course, except 0. Okay? So if we have 2-dimensional space now, the robot has 2 coordinates, x and y. So the function, the f of x will not be f of x anymore. It will be f of x and y. It's a function of 2 variables. And based on the value of these 2 variables, x and y, these 2 coordinates basically, f will have, will have some specific value. So to generalize this, we do in that way. F attraction of x and y, because it's a function of x and y generally, is equal to the constant, which we call zeta here, multiplied by, this is called the norm. Okay, just ignore that for a moment. Of x minus xg to the power square, so the current coordinate of the robot minus the x coordinate of the goal plus the current y coordinate of the robot minus the y coordinate of the goal. Simply, there is a typo here. Just remove this this norm for now. Okay. So how are we gonna do that? Okay, we'll do that after the picture. So just ignore this. Oops. Ignore this norm for now. Okay. So the basic, equation is something like zeta, and then norm of b minus b goal. And b goal, b is actually a vector of x and y, and this is another vector of xg and yg. And basically, this norm here will be written in that form. That's it. Okay. So some basic example here in 1D. If the goal is at 50, x equal to 50. So this can be your attraction force. 1, zeta is equal to 1, multiplied by x minus 50 to the power square, where goal is at x equal to 50 and zeta equal to 1. Okay. So this is basically the attraction force. So this is step 1, is to create attraction force. Step 2, to create, so this attraction force will attract the robot towards the goal. Step 2 is to create a repulsive force. A force that will push away the robot away from the obstacles. Okay. That's good. So basically, as we say, for the attraction force, the minimum is at the goal. Here we have something similar. The maximum of this function should be at the obstacle. Okay, so the robot will not be confused. It all the time go away from the high values of the function and move toward the low values of the function until it reaches the minimum of this function. Okay. So rho of x here is just, so basically you can say f of x, if repulsive, is equal to 1 over x. You can say so. This is a very simple form of this repulsive force. Okay, so for example, if this is the axis x, if there is an obstacle at x equal to 0, the shape of this function 1 over x will be something like this. The problem is that function, that math formula now, that equation, have infinite value as the obstacle. And when we make coding, we usually avoid such infinite values. Okay, that's why we don't put x directly here. We say f of x equal to 1 over rho of x, where rho of x, another function is, it's also a function of x. Okay, but it avoids this infinity values. That's why we don't put 1 over x directly here. And what is this thing here? 1 over d naught. So basically we say that if the obstacle, for example, at x equal to 0, this function will operate only from x equal to 0 until x equal to d naught. Other than that, it's 0. So if repulsive for x larger than d naught is equal to 0. It has values only between 0 and d naught. That's what's written in here. And this constant eta is just a parameter, just like the one we saw in the previous slide, which was zeta 0. Okay, you can play with, you can choose it whatever you want. Just like you choose by yourself the repulsive force. This is just one example for it. You can choose it with whatever you want, but you need your choice, your functions that you will choose, okay, should have high values at the obstacles and zero outside the d naught. And you also can choose d naught by yourself. And you may also say, I don't want this, this restriction on the, I can assume that d naught is just equal to infinity. So this function can operate all over the map because 1 over infinity is just 0. So at that case, if r of x and y equal to eta 1 over rho of x. You can choose it in that way as well. That's fine. Okay. So we have two forces now. We have two functions. One represent what we can call attraction force that attract the robot toward the minimum, and its minimum is at the goal location. And another function which represent what we can call repulsive force, a function that push away the robots away from the obstacles. So it has high values near the obstacles. Okay. Now, since in the first example that I showed you in slide 1 or 2, we were talking about only one function. So this function, this whole function, is actually the addition or the summation of both functions together. So FA plus FR. Remember the first one, it has the minimum at the goal location. But maybe at some location which has an obstacle, it has some low value, small value. So if you don't have obstacles, you can use only FA, F attraction. Because it has no restrictions. It has no definition for the obstacle. Maybe you have some obstacle and FA at that obstacle is not 0, not the minimum, but low value. Maybe close to the minimum. So maybe the robot will confuse and go to that obstacle thinking that it's the minimum, the global minimum or the general minimum of the function. So that's why we created the F repulsive. So both together, FA plus FR will have the two characteristics: pushing the robot away from the obstacles and attracting it toward the goal. Okay. This, this summation of the two functions, if you take the gradient of that summation, this gradient should have one minimum at the goal location, just like F minimum, F attraction, just like this. And this minimum should be at the goal location. Then, when you calculated the gradient, you just follow this algorithm, this very simple algorithm here. Okay, it's really simple. If you look at the coding, it's just 10 lines. If you look, for example, depth first search or breadth fit, maybe 30 or 40. It's really simple. Okay, so what we're gonna do exactly after summing up both function, F attractive and F repulsive, this is the final step. Now we calculate the gradient of the function. There is a typo here. The gradient should be nabla, not delta. Yes. Okay. You calculate the gradient, the minus of the gradient, and let the robot, follow the opposite direction of the gradient, or the direction of minus the gradient. Okay, we can say so. So for example, Let's assume that our robot is moving along x-axis. Okay, and this is f. This is a summation. Let's assume so. And here is the goal. So the robot, if the robot was here, if this is the start point, the robot should move in that way. And if the robot starts from that side, it should move in that way. Good. So how this algorithm is making sense to us? Let's explain it. We are saying you should move in the direction of the negative of the gradient, okay, which is the direction of the opposite to the direction of the increment of the gradient, or the increase of the gradient. So if we are on the left of the goal, we move toward x. Let's see how this is related to the negative gradient. So if we take 2 points on that curve here, part of the curve, and this is a tangent, the first one, this is slope 1, and this is a tangent of the second point, this is slope 2. Clearly, slope 2 is larger than slope 1. That means the gradient is increasing in that way. So you move up in the direction of minus x. So the robot should move the opposite of that direction. And that's the case here. The direction should move in the direction of positive x. Let's do the same for the other part of the curve. If the robot was here, it should move in the direction of minus x this time. So let's do it again. So let's take this point, for example, and let's draw the tangent. This is slope 1. This is another point here. Slope 2. Again, slope 2 is larger than slope 1. That means for that part, the gradient is increasing in that way, in the positive x. So the robot should move in the direction of negative x. Okay. Another observation, if you don't want to see if it's increasing or decreasing, you can look at the sign of the negative of the gradient. You see, guys, this blue line here, this blue line is actually the negative of the gradient of f of x. You see, this is the 0, and this is here 0. So all these blue values are actually positive. Which is the same. So we can say let the robot move in the positive x direction. If we look on that side, all between 0 and this point, all the values of the gradient are negative. So we can say let the robot moves in the negative x direction. So you can look at the sign of the negative of the gradient, or where is it increasing, in what direction it's increasing, or what direction it's decreasing. Okay, and you move with the direction of the decrement of that negative gradient. Okay, so let's do an example, just with real example on some real map. So let's stop the share screen. Stop this guy for a moment. Keep, yeah. Okay, let's have this example that we just explained to you. is 100, 90, 80, 70. Okay. So let's have our robot here at x equal to 0. So starting point is at x equal to 0. And our goal is at x equal to 50. We'll do it step by step. Okay. So step 1, and you have no obstacles. No obstacles. Since no obstacles, so F is equal to only FA. So we need to create, you know, attraction force or attraction function. Basically, the simplest one is 1 multiplied by x minus xg squared. So 1, of course, multiplied by anything is just 1. It's just the same thing. So x minus x goal, I'm sorry, which is 50 squared. Okay, this is our F now. And there is no repulsive force. Okay. Now let's calculate the function of the gradient. So this is f of x. Number 2, minus gradient f of x minus d x minus 50 squared by dx. This will be equal to 2 minus 2 x minus 50. Yeah, that's it. So minus gradient f of x is equal to minus 2 x minus 50. Number 3, step 3 is, you know, to follow the algorithm that I just write, but I didn't explain. I thought it's better to explain it with a real example. Okay. So we're gonna loop. Okay. And each time we start from the starting point, which is at x equal to 0. And at each time we look at the direction of the increment of the gradient. I'm sorry, the decrement of the gradient, or simply the sign of the negative gradient, and we move in that way. So we say that x new, the new location, is equal to x old, the old location of the robot, plus some constant. This is called the velocity constant, multiplied by I will just write it, okay, then explain. By this, you know, term here. First of all, this constant is another parameter, a third parameter now, okay? We have a lot of parameters today. I'm trying to make it very simple for you, but, you know, but, you know, you will study it and you will find it doable, okay? This is called the velocity. I will explain why it's called the velocity when you go to the code, okay? But it's basically a parameter that you can choose. So I will choose the constant or the velocity constant equal to 10. You can choose it with whatever value you want. No problem at all. Okay. So let's choose it equal to 10. So let me change the paper size to A3. Yes. To make it bigger. And let's see what we're gonna do. So x new equal to x old, which is 0, plus 10 multiplied by the negative gradient of x old. So this is actually the negative of the gradient. Just remove x and put x old. So minus 2, 0 minus 50 over. This is called norm 2. Norm 2 of any function can be also simple. It has another symbol called these 2 bars here is actually equal to the square root of f of x squared, which is basically f of x. It will be more complicated if you have 2 variables. You will not find it simple like this. But this is one-dimensional problem, so you can have such kind of simplicity. Okay. Good. So basically, let's apply it very accurately, just to make it easier for you to follow. So minus this is the minus here. So minus 2, 0 minus 50, and this should be squared. Okay. So what is this gonna be? It's 0 plus 10 multiplied by. It is basically positive 1. It will be positive 1. Okay. So x new is equal to 10. So let's ask so this is a new location of the robot. So the robot will do such a calculation, very simple calculation. It's really very simple. Okay. And based on that, he knew that he is standing at or stepping at x equal to 0. He should go to x equal to 10. So after the first step, the robot will come at that point. Then he will ask himself a question. Is this the location of the goal? Apparently, the goal is at x equal to 50. See, so he will do or repeat that again. He will not do anything new. He will just repeat what he has done. But he will replace x old by its new location, which is 10. So now, since this is not the goal, so x old equal to x new equal to 10. And just repeat again this step here. So let's repeat it. So let's do any new step, or any repetition step with another color. So x new equal to x old, which is 10, plus 10 multiplied by minus 2, 0 minus, and now 10, I'm sorry, minus 50 over square root of minus 2, 10 minus 50 square. This is again plus 1. That's it, positive 1 or 1. Okay, so x new will be equal to 20. X new equal to 20. So the robot now, based on this simple calculation, will move to x equal to 20. So this is step 1. Now this is step 2 here. Then the robot will ask himself the same question. Is this the goal location? No, it is not. So it will repeat the same step again. But first, replace x old by x new. So x old will be x new equal to 20. Then let's do that again with red, for example. So x new equal to 20 plus 10 multiplied by minus 2, 20 minus 50 over square root of minus 2, 20 minus 50 square Again, this guy will be all the time, it will be just 1. Because it's 1 dimension. And if it's 2 dimension, it will not be that simple. Okay? So this will be equal to 30. So x nu is equal to 30. So the robot now will move to x equal to 30. And again, this is not the goal. Not the goal. So x old equal to x new. And repeat again. Let's do with this gray. So x new equal to 30 plus 10 minus 2, 30 minus 50 over square root of minus 2, 30 minus 50, all that squared. Again, this guy is just 1. This is equal to 40. So x new is equal to 40. Again, not the goal. So x old equal to x new equal to 40. But we are very close now. I will see. So now x new is a 5th step, 5 steps, equal to 40. This is 40 plus 10 minus 2, 40 minus 50 over minus 2, 40 minus 50. This is again plus 1. 40 minus 10 is equal to 50. So now x new is equal to 50, which is equal to x goal, or the goal location. So at the 5th step, I'm sorry, we forgot the 4th one. So this is the 4th step. And now in the 5th step, the robot has reached the goal. Okay. So basically, this step here, this, this big function here, that, look, you may get afraid of it, is basically gives you a sign, +1 or -1. Okay. If you started your journey from, for example, x equal to 100, if this is the starting point, this term here will be equal to -1. So you can move in the negative x direction. In that example here, we started at x equal to 0. This is +1 means move in the positive x direction. Okay. One thing here, I said that you can choose the velocity. This constant, you can choose it with whatever value you want. We choose it equal to 10, and we reached the goal in 5 steps. What if we choose it equal to 25? Anybody guess how many steps we will need?
2 steps.
Yes, 2 steps. If we choose the velocity equal to 25, we will move. So let's do that with some colors. Red, for example. So we start from here. Then we will go to 25, step 2. Then step 3 will be here. Some may say, okay, let's increase it then 25. Okay. How about 30? How many steps?
Would you get an error if you did that?
Yes, that's right. Yeah. If you choose a 30, so let's do another, color. After the first step, you will reach this point, but then you will reach 60 here. And whenever you reach that point on the right of the goal, when you calculate it in the step, this step you will find this is negative. So you move back, but since the speed is 30, you will land again on 30. Then you go to 60, then you go to 30, then you go to 60, then you go to 30. You know, an infinite loop. So the best locations that the closest locations that you can land using a velocity of 30 is 60, because this is just 10 steps away from the 50. This is your best solution. So one feature of that solution is that you are not, you know, because you can choose this constant with whatever value you want. It's not guaranteed to reach to the exact point of the goal. You may have some bouncing around. Okay. And if there is no in that particular example with velocity equal to 30, if you leave the while loop with no braking, with no condition for braking, it will continue forever. 60 30 30 60 60 30 30 60. So in that particular problems or algorithms, we also put, you know, a higher limit on the number of iterations, because we can, you know, loop forever. So you will reach your goal with some error. So you must have some tolerance to say that if this is close enough to the goal or not. And you must have some condition to break the loop if the loop something wrong happened with it, and there is some bouncing around the goal with no, you know, is no acceptable tolerance or no acceptable landing location, we can say, near to the goal enough. Okay, so this is basically the algorithm. This is, you know, yes, it's a control system. So somebody here is asking if it's, yes, something very close to a control system. Okay, so let's do the example that I just solved with you by hand. We can also do it in MATLAB. Okay, and of course we can do can change many parameters easily without needing to calculate by hand. So MATLAB will do everything for us. So let's share the other screen. You can see my MATLAB, guys, or not?
Yes.
Thank you. So this is Mr. MATLAB here, okay, our big friend and the close friend also, because he is making everything is easy for us. Believe me, such kind of algorithm in C++ would be horrible. But anyways, okay, so we have here our problem. Okay, our space is just, you know, x-axis from 1 to 100. This is our space. Okay, we just move along x-axis between 1 and 100. This is our space. The goal is at x equal to 50. So we choose our attraction function in that way. Okay, using that way, it will be like a parabola, and this parabola will be centered at x equal to 50. Good. And there is no obstacles, so we don't need f repulsive. I'm just, you know, giving that example in the beginning, so, you know, you will grasp the main idea. Study it well. Then on Thursday we will take the multi-dimensional one. So it will be two-dimensional. It will be much harder to visualize. But anyways, okay. So here I am defining the maximum number of iterations, because maybe you choose some variable in a bad way, so it may bounce around with very high error, larger than the tolerance here. Okay, so you need some condition to break the loop. This variable called tolerance is actually how much error is acceptable for you. So for example, if the goal is at 50 and your tolerance is 1. So if the robot reaches a point somehow between 49 and 51, for example, 49 and 0.5 or 0.4, whatever, or 50.6, that's good, because the difference between 50.6 and 50 is 0.6, which is less than the tolerance. So this is another condition to break the loop. And again, both two variables or parameters is based on you. It's your choice, okay, as a designer. The speed or the velocity that the variables that I explained, I put once 10, once it was 25, once it was 30, okay. Here it's 10. So I will just repeat the details that I have done with you in our example here. The start point is at 1, just like our example. And we will change it later and see how this will change the solution. Okay. So first, we will set the current position of the robot to start. Okay. And route here is just a vector which will contain all the points that the robot will land in its direction or its journey to the goal. Which, for example, at speed equal to 10 or velocity equal to 10, it was 1, 10, 20, 30, 40 until it reaches 50. In the fifth step. Good. The good thing about the MATLAB is that you don't need to do the gradient by hand, then apply it or write the equation in MATLAB. Just write minus gradient of f. That's it. You don't need to, doing the derivative yourself, the exponent goes down, -1, the exponent, all such details, all these hectic, steps are not required. You can just write gradient. This is a very good function in MATLAB, which will get the gradient of the function f. Okay. If you don't want to use gradient, this function called the gradient, you can do it in that way. So let's do a comment here. This is equal to -1 multiplied by what was, oh yes, it was -2. Yeah, it's -2 multiplied by x minus 50. This is exactly that. This is if you make the derivative by your hands and apply it in MATLAB, but you don't need to do that. Just write the gradient of f, and remember we need minus of the gradient, so multiply in the beginning by -1 here. Okay. Then this will give you what you want exactly. Good. Then I will plot just the x and the gradient of x. I will draw the point of the goal. Okay. I will do a run with you with this, but just explore the code itself. Here are the two conditions in the while loop. If the iterations is larger than 0, continue. So basically, I will decrease the iterations by 1 each time I go into the loop. And if the goal if the current condition position of the robot minus the goal location is larger than the tolerance, then also continue the looping. Other than that, exit the loop because you reach it close enough to the goal. Good. First, I am calculating gradient minus gradient f of x of current location. Okay, so this this line of code here, if we go back to the tablet, I just can grab this. Yes. So this step here is actually this step. The numerator here. Okay, nothing new. I'm calculating minus gradient at x old or the current location. X old here is the current location. Okay, good. Then I am doing this big term, which is actually, this step is called normalization, because we don't need the value. We need only the sign, positive or negative. So this step here is actually this step, this big step. Okay, in which case, because it's one dimension, it will just positive 1 or negative 1 based on the location of the robot. Okay. Now, here is, x new equal to x old plus the velocity multiplied by this vector. So this line of code here is actually this one. This term. It's exactly, but encoding. Then after that, I will assign the current or x old x equal to x new. That's what I'm doing. Okay, I am drawing the new location of the robot. Then just make a pause so that we can track each step, the location of the robot. It's just MATLAB. It's not part of the algorithm. Add this new location to route and decrease iterations by 1. Then go back here. If the current position is close enough to the goal, I mean this subtraction is less than tolerance, then exit. Other than this, continue again in the loop. Okay, so let's run and see what we have here based on that coding and the choice of these numbers. So let's run. So first I am just drawing to show you that the function that we chose, if attraction has a minimum at x equal to 50, which is the goal. Okay, good. Now we're gonna draw, yeah, this is the minus gradient of x. If you notice, so let's continue here and plot the grid. Yes, if you notice, this is the 0 line. And all the values here of the minus of the gradient of x, this dotted blue line is actually the drawing or the plotting of minus gradient of f of x with respect to x. All the values here are positive. That means if the robot is here, he should go in the positive x direction. And all the values here are negative. That means if the robot is on the right of the goal location, he should go in the negative x direction. Okay, how we done this, how we get such a kind of very neat property, because of the choice of the f attraction function. The choice of this function is very important. You cannot choose any function, and you just play. No, it should have a minimum, for example, at the goal equation. Basically, quadratic functions will do that job for you. So it's not a arbitrary function. Okay, you should choose it wisely. Good. So let's continue and see. So we go now to the loop. First, we calculate minus gradient f of x old. So then we calculate this big term that will give us positive 1 or negative 1. As you see, it's positive 1. Okay. Then we calculate x new equal to x old plus the speed or the velocity multiplied by this big term. Okay. So x current position is 1. So we're gonna add. I'm sorry. We started here from 1, not from 0. But let's do it 0. I'm sorry. I will do it 0. Then also we'll have a problem with. No, we'll not have a problem. Can just do it. Yeah. there will be no problem. Okay. Sorry guys for this. Yeah, no problem. Yes, no problem. Oops. It goes to the, it meets the first loop. Sorry again. Good. So to this, then this. Okay. Okay. I just changed the starting to 0 just to make it exactly the same as our example. But that's fine. Okay, so this is whatever. After making the normalization, it will be +1. Then current position is again 1. What? They change it. Oh, the start. Oops. The start should be 0. Again, I am very sorry. Okay. With debugging, everything is fine. Start again from the scratch. Okay. Slowly. Okay, block the grid, enter the loop. What? Ah, yeah. This is because of the 0 stuff. Yeah, that's why I started from 1. Because again, since you choose this function, it may have this, gradient of 1/0, for example. So you should start from 1. Okay, that's the problem, It's just a math problem. It's not basically a problem with the algorithm. It's math problem. So you should re-choose make some modification to your function so that you can avoid this. So that's why I started from 1, but it doesn't matter. It will give us the same stuff. Okay, so let's continue here. Okay. Now the current position is 1. The speed is 10. Okay. And this guy is 1. So boom. The new location is 11, not 10, because we started from 1 now. Okay. So we just shifted by 1. So equating current position to new location. Then continue, plot this. So we started from 1. Now we are at 11. We continue again. Oh, yes, I should put this down. Okay. We continue. Of course, current position is 11. Goal is at 50. The subtraction is 39. It's much larger than the tolerance, which is 1. So I'm just continuing. Okay. Now we will be at 21. It's exactly the same example, but we shifted by 1. Okay. Now 31. Keyboard. Then 41. 41. And then we'll go to 51. So 51. So look, this is the new location. So this is the goal, and here is our robot at 51. Okay, can remove this pose because anyway we walk line by line, so that's fine. Okay, then yes, there will be a problem because we changed it, but that's fine. So we continue looping because 41 minus the goal, which is let's make it larger than or equal to, so that it will stop at that point. Good. Yes. So we run it one more time. I just made this program just before the start. This small program. I wasn't intending to do the big one first, but I said that if we do this simple one, it will be easier for them. So that's fine. So we will do it again now. Okay. So the first step. Why is there is a pause? Oh. This should work now. Okay, so this is the first location, first step, second step, third step, fourth step, then fifth step. Now we are at 51. 51 minus 50 is equal to tolerance. So this condition is not yeah, it should exit, right? Let's see. It's again this infinite loop. 12. So less than or equal. Larger than. $51 minus 50 is 1. 1 is not larger than 1. So it should exit. Why it continues? We have a problem somehow.
Oh, because your iterations. You have a
Yeah.
You have a set to,
I should make it or, right?
yeah, or
Yes. Okay. Okay. Thank you very much. Yes. Okay. Yeah. So let's see. Yeah. We should exit if one of them is satisfied. Yes. Is not satisfied. Okay. So let's see. So at 41, 51, let's continue and see. What? Why is that? Let me do it in the, in the easy way. If the first one is very confusing, so let's do that in that way. So if that less than or equal to tolerance, we're gonna just break. Okay? And let's see what we will have. I'm very sorry guys for this. Okay. Okay. Then 41, 51. The moment of truth now. Yes. And we just exit. Okay. If we look at route here, actually it will print out. So these are the points that we landed in. We land on one is our first node, then 11, 21, 31, 41, then 51. Okay. I'm very sorry for, making it very long, but this is, the best way to avoid any confusion. Okay, let's now change the speed. So let's do, for example, 20. Okay, let's see what's gonna happen. So let's exit this. Let's, put that on our side here. And yes, okay. Continue. I should also plot the start point. What? Good. Yeah, so this is a start point. Then after the first iteration, we reached 21, right? Yes, 21. Because the velocity of the speed is 20. Then we do the third iteration, it's 41 right now. Then look at here. So it's 61 now. So 61. I will continue. So if we look at this, it's a positive one, okay? Because we were here and this is on the left of the goal, so it's a positive one. Now we landed here on the right of the goal. This should be -1 in the next iteration. So let's see what's gonna happen. Of course, 61 minus 50 is much larger than 1. So we will just continue. Okay, now let's see this guy. -1 now. So move in the negative x direction. What's gonna happen? We're gonna go back to this location at 41. Okay. Good. Then now we are at 41. This guy is positive now because we are on the left of the robot of the goal location. So we should move in positive x direction. That's why it's a positive 1. And we will land is 61 right now again. So this is 61. So we moved from 41 to 61. When we are 61, we will move to 41. So this is the bouncing that I am saying. Okay, you may bounce around the goal location. That's why you need this iteration here. If there is no iteration, you will go into the loop and you will just continue forever, because the tolerance that you set always not this condition for the tolerance for the accuracy is not satisfied at all, and you will just bounce between 41 and 61. So the designer or the programmer of such algorithm should choose carefully the speed, this parameter here. Not all values will be good. If you don't have any idea about a good value for the speed, okay, then he should put this maximum number of iterations so that the infinite while loop will be, will not happen, cannot happen, okay, and after some iterations it will exit. Good. So let's choose, for example, let's start, for example, from let's do the start at 80. Okay, and let's set the speed. I'm sorry. Let's start at 80. Let's set the speed at 10. Again, let's see what's gonna happen with this. We are starting from the right of the robots. We are moving in the negative. This guy will be negative. Okay, let's see. And we will reach, let's see. Yeah, we are exactly on the goal. And we break. Okay. So the choice of the constants, like the speed, for example, might affect your solution. Okay. Let's choose the velocity with just 1. So here we reached the goal in what step? 1, 2, 3, 4 steps. What if we choose a speed just 5? Let's say 5. So let's see what's gonna happen. Oh, 8 steps. So let's make it 1. Very slow. That's why it's called speed, because it determines how much speed, or with how much speed your robot will reach the goal, or your algorithm will finish. Okay. Good. This is just another running of the algorithm. So high values for the speed will make the robot reaches quicker to the arrives quicker to the goal, but it might bounce around. Small values for the speed, okay, will make the robot reach the goal, but in a much slower rate. But you will avoid such bouncing around. And by the way, you can choose the goal. I'm sorry, the speed. Where is it? With something less than 1, for example, 0.1. Okay, let's see how much. Good. So size of route. How many points we landed on? We landed on 292 points. If you look at the graph here or the plot, look, it's very dense because there are many points that you landed in. But how about the accuracy? So the last point in route is actually 50 points. The closest one is 50, 50.9. 50.9. But you needed 92 or around 100 steps. If we take the speed equal to, let's say, where is it basically? 25, let's say. Oh, you know what's happening? You know, it's again this bouncing. And the closest location to the goal is 55. So 5 steps away from the goal location. But you needed only maybe 1 step, just 1 step to reach to that location, 55. 1 step only, you are 5 steps away from the goal. But then you bounce it. So it's a kind of trade-off. If you choose a small value for the speed, you will reach the goal in a very slow rate, but with higher accuracy. If you choose very big speeds, you might reach to a close, to some close location to the goal in a very fast manner, but you cannot make it, you know, closer, for example, or the error might be high, okay, or not acceptable at all for you. So it's a trade-off. That's why it's called the fine-tuning of parameters. You need to play with the parameters to choose not a very slow value, not a very small value to avoid the slowness in reaching into the goal, and not very high values, with, of course, that will make you reach faster to the goal, because this might end up with a very bad accuracy for your. So you must make a fine-tuning, something in between, we can say, okay, not big enough, not very big or not very small, so you can reach the goal fast at the same time with high accuracy. Like, for example, if you choose the velocity with 25 or 10, with 10, let's see, 1, 2, 3, only 4 steps, good enough, and you actually reach the goal exactly 50. It's much better than 0.1. Okay, so it's something in between. Okay, guys, so this is basically the simplest version problem of the artificial potential field, please study this code very well, because and this lecture as well, the slides that I will send you after this lecture, because next time we'll have a broad view of it with a map, with a 2D map. So you must visualize, you must have this background in your mind so you can visualize easily what's really happening in a 2D map. Okay, it's not easy to imagine if you don't have such background. Okay, any question, guys? Any questions? Okay, so see you next Thursday. Have a good day. Bye-bye.